Dear students, we are discussing about ray optics, in which we are going to speak about the formation of real and virtual images by plane mirror. Let us consider a plane mirror in front of which, actually this is how a mirror must be represented. One surface is fully silvered, the polished surface will reflect the light falling on it. Let us consider a real object which is placed at a point O. The rays falling on the mirror after reflection will diverge or will go out from the plane mirror. When the rays are produced backwards, they meet at a particular point, let us say I, behind the mirror. So we can say here the rays after reflection appear to diverge from a point behind the plane mirror. Appear to diverge from a point behind the plane mirror. The point I from where the rays appear to diverge is called the image. As it is formed behind the mirror, we call it virtual image. Because it can be seen through the mirror, but when you go on to see behind the mirror, you cannot see any image. This kind of image is called virtual image. So, for a real object, a plane mirror produces a virtual image. So, we can simply say here, a point O is considered, that is supposed to be a real object from where light rays are diverging out. They are falling on the plane mirror. After reflection, they are still spreading out. When they are produced backwards, they meet at a particular point I behind the mirror. The point from where the light rays appear to diverge. See this one, they are not diverging from this point. They appear to diverge. That's why I have shown here dotted lines. The point from where the light rays appear to diverge from a point behind the plane mirror is the point where the image is formed. We used to call it the virtual image. So, this type of image, which is formed behind the plane mirror, which cannot be obtained on the screen, but can be seen with our eye, is called virtual image. So what is a virtual image? An image which is formed behind the mirror, which cannot be got on the screen, and which can be seen by the eye. You can see it, but you cannot get it on the screen. And it will be formed behind the mirror. This kind of image is called virtual image. Then what about a real image? So a real object produces a virtual image. What about a real image? How will you get a real image? We can say here a plane mirror is considered. A convergent ray is made to fall on the plane mirror. See this one? A convergent ray. This is a convergent ray. Appears to converge. A convergent ray appears to or is made to fall on a plane mirror. After reflection, the rays will converge at a point. After reflection, the rays will converge at a point in front of the mirror. Rays are converging at the point in front of the mirror. These convergent rays, when produced backwards, they meet at a point O. We used to call it the virtual object. So you cannot see the object, or you cannot identify where the object is. Where the object is there in front of the plane mirror. But the rays coming from the virtual object after reflection from a plane mirror will meet at a point in front of the plane mirror. We used to call it the real image. We used to call it a real image, I. And this image is formed in front of the plane mirror. So this image can be caught on the screen, can be obtained on the screen, and also you can see this image. So this type of image which can be formed on the screen, also which can be seen by our eye, is called a real image. What exactly happens is that the ray appears to converge at a point O, but not exactly happens. That's why we are saying convergent rays. This convergent ray, after reflection from a plane mirror, will meet at a point. That point is there in front of the plane mirror, and the image formed there is the real image. So a virtual object will produce real image. It is very well known that we used to understand, we always consider that a real object will always produce a virtual image. But there is another condition, that a virtual object will also produce a real image. A virtual object will produce a real image. We can consolidate the kind of rays produced from the objects and respective images which are dealt with the plane mirrors, so that while having discussion related to objects and images, we can have a clear picture about the kind of object, the type of object and type of images. We shall speak about the nature of objects and images and the conditions of the rays associated to the object and image. When we speak about a real object, rays actually converge from the object. Rays actually, diverge from the object. You can see the diagram. Rays actually diverge from the object. This is for real object. What about a real image? For a real image, the rays actually converge. The rays actually converge at the image. Rays actually converge at the image. See this condition? Real object. It's the point from where the rays actually diverge from the object. You can see the diagram over there. The rays actually diverge from the object. For a real image, the rays actually converge at the image. Then for a virtual object, the rays appears to converge at the object. The rays appears to converge at the object. You can see the diagram. You can check out the diagram. Then for virtual image, the rays appear to converge at the image. Rays appear to converge at the image. See the statements. For a real object, rays actually diverge from the object. For a real image, the rays actually converge at the image. For a virtual object, the rays appears to. This is actual, it's happening, and this appears to. It appears to be happening. Rays appears to converge at the object. And for virtual images, the rays appear to converge at the image. If you are very clear with these conditions, you can easily identify the nature of the object and image, whether it is real object or virtual object, or real image or virtual image. We shall see an example problem here, 6.2. What is the height of the mirror required to see a person fully himself from the mirror? Question is very simple. What is the height of the mirror needed to see the image of a person fully on the mirror? Let us draw a simple diagram here. A plane mirror is considered. A screen. Can consider this as a screen. This is a plane mirror. Let us consider a person who is standing in front of the mirror. H is the head of the person, E is the eye of the person, F is the feet of the person. A person can see his head after the light ray getting reflected from a plane mirror. Light ray from the head travels and falls on the plane mirror, and after getting reflected from the plane mirror, he can able to see his eye. Let us say h1 be the height between the head and eye of that person. Then the light ray from the feet after reflection will also reach the person's eye after reflection. So he could able to see his head as well as his foot at this through his eye when the light radiations get reflected from this particular points. These are the points of incidence of these two reflections. Let us say h2 be the height between the eye and the feet of that person. If I am drawing a normal to the point of incidence, it acts as a perpendicular bisector between the angle made between the incident and reflected rays at the extreme reflections. You can see here, this is the head, this is the feet, the light radiations are incident at this particular points and they are getting reflected and reaching the eye. So, as per the law of reflection, I can say here, the angle of incidence and angle of reflection are the same. So, I am marking this as I1 and I1. The angle of incidence I2, angle of reflection is also I2. At the extreme reflections, this perpendiculars or the normals which are drawn to the point of incidence acts as the bisectors of the angle between the incident and the reflected rays. Incident and reflected rays. When the reflected rays are produced backwards, this is the direct ray from the head passing through the plane mirror, perpendicular ray. When this ray is produced backwards, it meets at this particular point so that the image H prime will be formed, what we can call the head of the image of that person. Similarly, when a direct ray is considered, it will produce the image of the feet. When this is produced backwards, it will meet at this particular point. So, we can say here, the head and the feet are formed over the screen, and the geometry of this particular mirror required to produce the image of this particular person is simply, you can just calculate here. If this is h1, this is h1 by 2 and this one is h1 by 2 because this is the perpendicular bisector of this particular incident and the reflected rays. So if these angles are equal, then h1 by h2, this height can be divided equally. h1 by h2, h1 by 2, h1 by 2. Similarly, this height is also h2 divided by 2 and h2 divided by 2. h2 divided by 2. What is the total height of the person? It is the sum of h1 and h2. So total height of the person h equals h1 plus h2. Now, you can see the perpendiculars drawn on the plane mirrors are at a separation h1 by 2 plus h2 by 2. This is the separation between the two perpendiculars drawn on the plane mirror. When you sum up, you will have h1 plus h2 divided by 2. This is equal to h by 2 itself. So what is the meaning for this? Geometrically, we are getting a result that the height of the mirror required to see the full image of a object is simply h by 2, half of the height itself. If a person is 6 feet tall, then the mirror required to see the full image of that person is 3 meters. Simple. So thus by geometry we are writing the height of the plane mirror required to produce a full image of the person is h by 2. Full image of the person is h by 2. Idea is very simple. So you are speaking about two reflections, you are drawing two perpendiculars and we are saying the height between the head and eye is h1, the height between the feet and the eye is h2, the total height is h, which is equal to the sum of h1 plus h2. That is different. After reflection, we can say the rays are reaching the eye of that person. So you are drawing a perpendicular. As per the laws of reflection, the perpendicular or normal drawn to the point of incidence acts as the perpendicular bisector of this particular angle made by the incident and the reflected rays. It divides the angles equally. So if this perpendicular is drawn, then this h1 can be divided as h1 by 2, h1 by 2. Similarly, this height can also be divided as h2 by 2, h2 by 2. As these rays are incident at these 2 points, this person can see this one? From the head, the ray reaches the eye of the person. From the feet, the ray reaches the eye of the person. So the total image is visualized by the person with his eye through this portion of the plane mirror. What is this portion of plane mirror? What is the length of this portion of the plane mirror? As per geometry, if this is h by 2, I can mark this as h1 by or h1 by 2, and this one is h2 divided by 2. When you sum up, you will get the total measurement, which is h by 2. So the height of the plane mirror required to see the full image of a person or full image of himself is h by 2. Does the distance between the person and the mirror has any relationship? No. Wherever the position of the person in front of the plane mirror is, doesn't matter. The plane mirror should possess a height equal to half of his particular height or her particular height. Then they can able to see the full image of themselves. So there is no dependence between the position of the person and the position of the plane mirror. So far we have had a discussion about plane mirrors. Now we are going to speak about spherical mirrors. Spherical mirrors are generally cut from the spherical surfaces. They are generally cut from spherical surfaces. They are generally made of glasses. The spherical surfaces are obtained from glasses. One part of or one surface is completely silvered, and the other surface acts as a polished surface from where the reflections takes place. If the reflection takes place from the concave surface of a spherical mirror, then we call it a convex mirror. If the same reflection, light radiation, falls on a spherical surface, a convex spherical surface, if reflection takes place from a convex surface, then the mirrors are termed convex mirrors. Generally speaking, a concave mirror always converges the light radiations falling on it. A convex mirror always diverges the light radiations falling on it. We shall see a simple diagram which will explain clearly about spherical mirrors. As I told you, spherical mirrors are obtained from, or spherical mirrors are generally cut from spherical surfaces. So what does this mean? So simply, for our understanding, we can consider the Arun ice cream. This is the usual example which I always used to give for the students to have a clear understanding about the spherical mirrors. Let us consider a ball ice cream which is available in the ice cream parlors. You might have seen the ball will be white in color and the cap will be in different color variants, blue, pink, green, whatever. So the entire arrangement is spherical in shape, on which the cap alone is a part. The cap alone is a part, or the cap is a part of that particular sphere. So we can simply say here, a spherical surfaces or a spherical glass is considered, then a part of that spherical glass surface is cut and removed from it. That will behave as a spherical mirror. That will behave as a spherical mirror. If you take the cap out of the ice cream ball, then that cap itself will act as a spherical mirror. So the nature of spherical mirror will be in that form. So from an entire sphere, we can see, we can cut two different spherical surfaces. When the inner surface is polished, then this surface acts as a convex surface. Convex surface. Because this surface acts as a polished surface, this is the reflecting surface here. This is the reflecting surface. If the outer surface is polished, Instead of showing a polished surface, I am just showing dashed lines which indicates that this surface is polished. So this is silvered, this is silvered. So the inner surface is polished. So this acts as the reflecting surface for this particular mirror, and this mirror behaves as a concave mirror. This mirror behaves as a concave mirror. If I mark this portion AB on the sphere, then this portion alone acts as a spherical mirror. I can mark this as A prime, B prime. And this C is the center of curvature of the entire sphere. C is the center of curvature of the entire sphere. So the center of curvature is the same for both convex surface as well as for concave surface, which is obtained from the same sphere. And it differs for different spherical mirrors obtained from different spheres. Kindly note this. If a sphere is assumed, from the same spherical surface, if a convex surface is taken and a concave surface is also taken, for both the mirrors, the center of curvature will be the same. If the sphere varies, if the dimension of the sphere varies, then the spherical surfaces which are obtained from those spheres will also differ. So the center of curvature will be different for those spherical mirrors. Now we are showing the convex surface as well as the concave surface on the same spherical surface, obtained from the same spherical surface. So if the inner surface is polished, means silvered, and the outer surface behaves as a polished or reflecting surface, then that mirror is said to be a convex surface. If the outer surface is silvered and the inner surface is polished or reflecting surface, then that spherical mirror is termed a concave mirror. We are going to discuss about some of the important terminologies which are related to the spherical mirrors. They are all very important to draw the ray diagram to obtain the images formed by this kind of spherical surfaces. We can list out one by one. First one, center of curvature. Center of curvature of a spherical mirror is the center of the sphere from which the mirror forms a part. What is the meaning for this? The entire sphere has a center. We used to call it center of curvature or center of the sphere. And a small portion is cut from the spherical surface or from the sphere. This portion of the spherical surface also possesses the same center. So we used to call it as the center of this curvature. Center of this curvature. So center of curvature of a spherical mirror is the center of the sphere from which the mirror forms a part, or in which the mirror forms a part. In which the mirror forms a part. That is called center of curvature. Then second one, radius of curvature. Radius of curvature. So I can show you with a diagram separately so that you can understand clearly. I am considering a concave surface. How will you identify a concave surface? Shall we say this is a concave surface? No, we cannot identify whether this is a concave surface or convex surface. So the nature of the surfaces will be identified only when the mirrors are silvered. If I silver the outer surface of this mirror, then this behaves as a concave mirror. Concave mirror. Now, this is the portion of a sphere from which this mirror forms a part. And for this particular portion, I can mark this as the center. I used to call this as center of curvature. And then, what is radius of curvature? Radius of curvature is the radius of the sphere. Radius of curvature is the radius of the sphere in which mirror forms a part. Radius of the sphere in which the mirror forms a part. So, radius of curvature of a spherical mirror is the radius of the sphere in which the mirror forms a part. The radius of curvature generally is represented as capital R. Center of curvature is represented with the letter symbol C. Then, We shall speak about the pole of the mirror. The pole of the mirror. We have taken separately the spherical surface from a sphere. Now the spherical surface will be in this form. See this one? In this form. Center of curvature is arbitrarily or is chosen at this particular point because this spherical surface is a part of the entire sphere. Assume there is a sphere over here and this is the spherical surface for which this is the center of curvature. Now, if the center is taken on the mirror itself, see this one? This is the mirror. I am taking the center on the mirror itself. And this geometric center or the center of the mirror is called the pole of the mirror. The center of the mirror is called the pole of the mirror. So, this is the cross-sectional view of a concave mirror. When you are representing it in the diagram, a concave surface is kept like this. This center or geometric center of the mirror. I am not speaking about the sphere. See the statement. Difference is very simple. See the terms what I am using. Center of curvature is the center of the sphere. Pole is the center of the mirror. The geometric center of the mirror is called the pole of the mirror. The geometric center of the mirror is called the pole of the mirror. If third one is pole, so the geometric center of the spherical mirror is called the pole of the mirror, which is represented by a letter symbol P. Radius of curvature is R, center of curvature is C. And then the fourth one is principal axis. Principal axis. Principal axis is a line passing through the center of curvature and the pole of the mirror. A line passing through the center of curvature and the pole of the mirror is called the principal axis. I can mark it as PA. So, line passing through, see, a line passing through the center of curvature and the pole of the mirror. Line connecting center of curvature and pole of the mirror is called the principal axis of the spherical mirror. Principal axis of the spherical mirror. So, the line joining the center of curvature and the pole of the spherical mirror is called the principal axis of the spherical mirror. A ray traveling along or passing along the principal axis after reflection from the spherical mirror, where the reflection will take place at the pole, because the principal axis is passing through the pole. Light ray is considered to be passing through the principal axis, passing along the principal axis. In the sense, it is passing along this particular line. After reflection, it will travel back and it will travel along the same principal axis in the opposite direction. The light ray will be traveling along the same principal axis in the opposite direction. So this happens only when the light ray is incident on the pole along the principal axis. So what is principal axis here? A ray or a line passing through the center of curvature of the spherical mirror and the pole of the mirror is called the principal axis. Any ray passing along the principal axis after reflection from the spherical surface of the mirror will travel back along the same principal axis. I told you, travel back. In the sense, it will get reflected back along the same principal axis. This happens when the light ray passes through the principal axis. Then, fifth one, focus or focal point. Focus or focal point. When a ray is made to pass parallel to the principal axis, after reflection, I can show you here, a ray passing parallel to the principal axis. After reflection, it will pass through a particular point on the principal axis. After reflection, it will pass through a particular point on the principal axis. We used to call it the focus or the focal point of the spherical mirror. So, the ray passing parallel and close to the principal axis after reflection will pass through a point on the principal axis after reflection, that point is called focus or focal point of the spherical mirror. I can mark it as capital F. Focus or focal point is marked as capital F. You should know the notations used for the respective terminologies. Then only you can understand what is what. If this is a concave mirror, the rays after reflection will converge at a point. I'll show you with a separate diagram. I can show it to you here. I'm showing you a concave as well as a convex mirror. For them, I can show you the focus or focal points. Let us consider a concave mirror here. This is the principal axis. This is the pole of the mirror. This is the center of curvature. And this is the principal axis, as I told you. Then, a ray passing or the rays passing parallel to the principal axis. As I told you, the rays are falling on a concave mirror. This is concave mirror. After reflection from the concave surface, the rays meet at a particular point on the principal axis. This point is called the focus or focal point or principal focus. Focus or focal point or principal focus. This is for a concave mirror. And for a convex mirror, rays passing parallel to the principal axis. Center of curvature is here, somewhere here. This is the pole of the mirror. This is a convex mirror. After reflection, the rays meet at a particular point on the principal axis. So it diverges from a particular point. See this one? Rays after reflection will appear to diverge from a point on the principal axis. We call it the focus or focal point or principal focus. So how will you give out the statement here? Rays passing parallel to the principal axis after reflection from a concave mirror will converge at a point on the principal axis. We call it the principal focus or focal point. Similarly, rays passing parallel to the principal axis after reflection from a convex mirror will appear to diverge from a point on the principal axis. Appear to diverge from a point on the principal axis. This point is called the principal focus or focal point of the convex mirror. So this is very important. And we can speak about focal plane here. Focal plane. If I assume a plane surface which is passing through the principal focus and perpendicular to the principal axis, then this is called focal plane. We call it focal plane. For this particular focus, I can draw a plane over here. It encloses or it passes exactly through the point. Actually, you may wonder, this diagram will create a small kind of confusion, but thing is quite simple. This surface is perpendicular to the plane of the board and passing through this principal focus. Just understand. This is the plane and this is passing perpendicular to the plane of the board through the focus. And this plane surface passing through the focus perpendicular to the principal axis. Principal axis is like this. This is the point where you are getting the focus for this concave mirror. Then this plane is called the focal plane. So, focal plane will be obtained in front of the concave mirror, and the focal plane for a convex mirror will be existing behind the mirror. Idea is simple. Then, after speaking about this focal plane, we have to speak about the focal length. What is focal length here? The distance between the principal focus and the pole is called focal length. The distance between the principal focus and the pole is called focal length. Here we can show the same distance here. Pole and the principal focus. This is the distance measured, small f. So small f refers to the focal length, capital F refers to principal focus or focal point. So the distance between the pole of the mirror and the principal focus is called focal length. It's called focal length. So what are the terminologies we are discussing about? You can see here, there is another relation which you will be deriving in the next sessions, that the radius of curvature R is equal to twice the focal length. Radius of curvature R is equal to twice the focal length. Radius of curvature is this one, capital R. So, what are the different terms or notations which we are using to understand, terminologies which we are using to understand about a spherical mirror? One is the center of curvature. Center of curvature is the center of the sphere in which a mirror forms a part, which is represented by letter symbol C. What is radius of curvature? Radius of curvature is the radius of the sphere in which a mirror forms a part, which is represented by letter symbol capital R. Then pole of a mirror. Pole of the mirror is nothing but the geometric center of the mirror, not the sphere. Pole of a mirror is the geometric center or central point of the spherical surface. Central point of the spherical surface, what is that? It is the geometric center of the mirror. Geometric center of the mirror. We call it the pole of the mirror. Then we have to speak about the principal axis. What is principal axis? A line passing through the center of curvature and the pole of the mirror is called the principal axis of the mirror. And we can say if a ray passing through the principal axis, passing along the principal axis, after reflection from the spherical surface will travel back along the same principal axis. So if it happens, then we can consider it as the principal axis. And then what is principal focus? When light radiations are made to fall on a spherical surface, after reflection it will converge or diverge at a particular point on the principal axis. The rays passing parallel to the principal axis after reflection from a concave surface will converge at a particular point on the principal axis. We call it the principal focus or focal point of the concave mirror. Then the rays passing parallel to the principal axis after reflection from the convex mirror will appear to diverge. See this one? Will appear to diverge from the point on the principal axis. We used to call it the principal focus of a convex mirror. Then what is focal plane? A plane passing through the principal focus. See this one? This is a curved surface. You can understand. This is a curved surface. Principal focus is somewhere over here. And this hand refers to the plane passing through that particular point. So a plane passing through the principal focus and perpendicular to the principal axis is called focal plane of the mirror. Then focal length. What is focal length? It is the distance between the principal focus and the pole of the mirror. It is the distance between the principal focus and the pole of the mirror. We used to call it focal length, small letter f. So C for center of curvature of the spherical mirror. R for radius of capital R for radius of curvature of the spherical mirror. Capital P for pole of the spherical mirror. Principal axis, and then principal focus, capital F, and then small f, focal length. These are all the terminologies which are very essential in understanding or in drawing the ray diagrams and to understand what is what. We shall now speak about the types of rays which are involved in drawing the ray diagrams. Let us consider a concave mirror whose outer surface is silvered. This is the principal axis, as you know. This is the principal axis now. And we can mark, this is the pole of the mirror, this is the center of curvature of the mirror. This point would be the principal focus of the mirror. This is the radius of curvature. This is the focal length. These are all the things which we need to know while drawing a ray diagram. Let us consider two rays. One ray, you can see A ray passing parallel to the principal axis and close to the principal axis. See this one? This ray is close to the principal axis. And also, it is close to the pole of the mirror. See this one? It is close to the pole of the mirror. And it makes small angle with the principal axis. This is the bisector. This is the bisector. And this makes a small angle. See this one? I can mark this as theta 1. Let me mark this as theta 1. It makes a small angle with the principal axis. This kind of rays are called paraxial rays. So what is a paraxial ray? A ray passing close to the principal axis. A ray must pass or travel close to the principal axis. And also it must incident close to the pole of the spherical mirror. And then after reflection, it must pass through the principal focus. Actually, this is the rule for drawing the ray diagram. As it is passing through the principal focus, it makes a smaller angle. Theta 1 is small. Theta 1 is small. If the ray makes a smaller angle with the principal axis, then such rays are called paraxial rays. Paraxial rays. What is a marginal ray then? A ray passing parallel to the principal axis, far away from the principal axis. See this one when compared to, this is paraxial, this is marginal. When compared to paraxial rays, marginal rays are far away from the principal axis. Also, they are at a far off distance from the pole. See this one? At a far off distance from the pole. After reflection, they make larger angles. See this one? This angle with the principal axis. I can mark this as theta 2. This is theta 1. This one is theta 2. This is the normal or the perpendicular drawn at the point of incidence. Actually, whatever the nature of the mirror is, whether it is a plane mirror or spherical mirror, laws of reflections are valid. So, the angle of incidence equals angle of reflection. You can see here a ray passing parallel to the principal axis but at a far off distance. See the difference? At a far off distance. And also, it is incident on the spherical mirror at a far off distance from the pole. And you measure the distance from the pole, it is at a far off distance from the pole. And also, it makes a larger angle with the principal axis. It makes a larger angle with the principal axis. So, this kind of rays are termed marginal rays. The behavior of this paraxial and marginal rays are entirely different. See this one? The two rays are not exactly passing through the same point on the principal axis. One is passing through F and another one is, paraxial rays are passing through F, and then the other ray is passing somewhere between principal focus and the pole. The two rays are not passing through the same point on the principal axis after reflection. Their behavior is entirely different. Their behavior is entirely different. One is paraxial and another one is marginal rays because they are getting two different focus. They are getting two different focus. So, we can say paraxial and marginal rays are, their behaviors are entirely different. Now, in our text, in our discussion, we are going to consider only the paraxial rays and not the marginal rays. Why? What is the purpose of selecting paraxial rays alone? Paraxial rays are making smaller angles, so that it will be very useful to make approximation with the angles. It will be useful to make approximation with the angles. How simply I can say here, for example, as this ray is very close to the pole of the mirror, I can consider this curved portion as a straight line. Curved portion as a straight line. That makes no difference while doing calculations. So, this happens or this can be done only when the angle made by the rays are very small with the principal axis. If it is large, you cannot. So, for our discussions, further discussions, we consider or we are taking only the paraxial rays for our discussions to draw ray diagrams as well as to speak about the images formed by the spherical mirrors, and we are now leaving this marginal rays. Now, I can sort out the difference between marginal rays and paraxial rays here. This one is paraxial rays, this one is marginal, so that You can keep this in your mind very simply. When compared to principal axis, it is, I can mark this as point 1, ray passing close to the principal axis. Here, ray passing far away from principal axis. Second one, ray incident on the mirror is close to the pole of the mirror. Here it is at far off distance from the pole, far off distance from the pole. And the third point is the paraxial rays makes small angles with principal axis. It makes, marginal rays makes large angles with the principal axis. That's all. This will give you a clear picture about paraxial rays and marginal rays. What are the things you are comparing here? How the rays are passing. When it is close to principal axis, paraxial. Far away from the principal axis, marginal. How they are incident on the spherical surface with respect to pole. When they are close to the pole, paraxial. Far away from the pole, marginal. What is the angle made by this reflected rays with respect to principal axis? If the angle made is small, paraxial rays. If the angle made is large, marginal rays. That's all. We will be discussing about the other ideas related to spherical mirrors in the next session. Thank you.